While you're getting your notes up, let me go over the objectives for today. Okay, today we're learning about Newton's second law. So our first objective is that you will be able to describe the law to me and apply it to situations. So you'll be able to tell me what is his second law and how does it apply to situations. And then to go along with application of Newton's second law, there will be two types of calculation problems you're going to do today. You'll need to be able to calculate the net force on an object, but instead of adding force arrows this time, I'm only going to give you mass and acceleration. And then the opposite of that, if I give you force and mass, you should be able to calculate acceleration for me. So not using our velocity and final velocity initial divided by time, but this time using force and mass. Okay? All right. And then the last thing we're going to do is talk about circular motion. So you will need to be able to describe for me how inertia and centripetal force affect circular motion. All right, we're going to jump in. We're going to take these plastic boxes that are sitting over here. You're going to attach a piece of string to your box. You're going to pull the box across a 2-meter section of the floor, forcing it to accelerate. So I want you to make it speed up as you move it across the floor. Then, I want you to put an object in that box. Try to find a weighty object, so you add significant mass to it. And then I want you to pull it across the same section of floor and try to match your previous acceleration. Okay? We're only going to take 5 minutes to do this lab. Let's discuss. What did you notice about the force required to accelerate the box with the two different masses?
Harder.
When is it harder?
When you have the thing on it. The weight.
When you put additional mass in your box, it requires more force from you to pull the box. This, and the lab we've been doing the last couple days in class, is a representation of Newton's second law. Okay? As you learned in the previous section, unbalanced forces are going to affect your motion. Okay? Objects at rest are going to begin to move in the direction of an unbalanced force. Unbalanced forces can change the velocity of objects that are already moving. All of these things are true about unbalanced forces.
I bet they make it deep in the planet.
Unbalanced forces can also cause velocity to change by speeding up. When the net force of an object is in the direction the object is moving, then that object will speed up. This makes sense, right? If you're driving a car and you push down on the accelerator and increase the force you are applying, the net force is going in the direction you're already traveling and your car speeds up. Another example, pushing somebody on a swing. Okay? If you apply the force in the direction they're swinging, then they will swing higher. You have sped them up. Unbalanced forces can slow objects down. When the net force on a moving object is in the opposite direction the object is moving in, then the object will slow down. Example, you're riding on a scooter and you put your foot down on the ground. That increases the backwards force of friction, which is in the opposite direction that you're moving. Now the unbalanced force is in the opposite direction of your motion and you begin to slow down. And of course, changing direction. Unbalanced forces in a new direction will change the motion of the object by changing the direction. So if you've ever played a game of pool, you have likely seen this happen. You can hit the ball with another ball and cause it to change the direction of its motion. Changes in velocity, also known as acceleration, are always caused by unbalanced forces. So anytime you're seeing an object experience a change to its velocity, you know that the forces on that object need to be unbalanced. Now let's talk Newton's second law. What does this actually look like? We've been doing a lab about it. We did the launch lab about it. What is Newton's second law? Well, Newton's second law says that the acceleration of an object is equal to the net force acting on the object divided by the object's mass. Okay? So you could write this another way. You could instead say net force on an object is equal to the mass of the object times the acceleration of the object. Neither one of these is wrong. It's just a different way of phrasing it. Whichever one makes more sense to your brain is the one I would keep track of. The equations look like this. For the second sentence, net force is equal to mass times acceleration. This is the one I learned. It's probably the one you'll see me use the most. F equals m times a. The other way you can write it is acceleration is equal to net force divided by mass. So acceleration equals force divided by mass. A equals F divided by m. Okay? These are the same equation, just written two different ways. So whether you're solving for force or whether you're solving for acceleration, they're just written slightly different so that you don't have to manipulate the formula on your own. Before we move on to circular motion, we're going to do a little example problem, okay? Just so you get a little practice seeing what this looks like. So we are going to imagine that I have we'll use the one from the book, a 0.5 kilogram basketball, okay? And I throw it with a force of 10 newtons, and they want to know what's going to be the acceleration of this ball. So because we have mass and force here, we're going to use that second equation. The acceleration is equal to force divided by mass. So we're going to take our force of 10 newtons and divide it by our 0.5 kilogram mass. And because newtons are actually, so the unit newton is meant to represent kilograms times meters per second squared. The kilograms will cancel and we will be left with an acceleration unit. So if we divide 10 by 0.5, we should get 20 meters per second squared. So this is the type of problem where you will use one of those equations. In the other type, with using the other formula, force equals mass times acceleration, I would have given you an acceleration and a mass, and you'd be solving for a force. Okay? All right. Now we can talk about circular motion. Okay? We're going to skip having you guys individually do this lab, and instead I will demonstrate to you. Okay. I have a stopper on a string. If the forces acting on this are just me pulling centrally on the string, so the string is pulling in towards the center of the circle, okay, and gravity is pulling down, okay, why doesn't the stopper just fly to the middle of the circle if that's the only direction that force is applied in it?
Because of the inertia from the
Exactly, because of the inertia of the stopper. Remember that inertia is the tendency of an object to resist changes in its motion, which means inertia would like this stopper to continue in a straight line. The stopper cannot continue in a straight line because it's being pulled towards the center of the circle, so instead it goes in a circular motion. If the stopper didn't have inertia, it would collapse to the center of the circle because the only force acting on it would be the string. Okay? This is how all circular motion works. An object's inertia causes it to move in a straight line path. A force is required to move the object in a circle or curved motion. Centripetal force is defined as a force that acts perpendicular to the direction of motion toward the center of a curve. Okay? People tend to think about the force in a circle pushing out, but that is not the case. Okay? That is just the inertia of the object not wanting to change direction. Okay? The only force being applied in a circle is towards the center of the circle, and we call that force centripetal force. Inertia, which is not a force, can cause us to feel like objects are pulling away from the center. For example, when you ride on a merry-go-round and you get it spinning really fast, you feel like you want to fly off. That is not because a force is pulling you off. That's because your inertia would like you to continue in a straight line. However, the only force in this situation is centripetal force, and that force is directed inward towards the center of the circle. All right, this is where our notes end today. Your homework is the 2.3 check for understanding, which I'm going to put up in just a moment.